In this video, I'm going to talk about some applications for vectors, and again, these are just made-up situations, but we can apply them if we ever need to figure something like this that's dealing with force or anything like that on an object. So first off, here it says Charlie and Gene Hughes are attempting to haul a large sign to the roof of their antique store. They are standing at the edge of the roof and pulling on ropes attached to the sign. The ropes make a 30-degree angle with each other. If Gene is pulling with a force of 105 newtons and Charlie is pulling with a force of 110 newtons, what is the magnitude and direction of the net force of the sign? So a lot of times in situations like this, I like to draw a picture. So here's our sign, okay? And one guy has a rope and he's pulling it this way, and another guy has a rope and he's pulling it from over here, and they're trying to hoist that thing up. And it says that the ropes formed an angle of 30 degrees. All right. And it also says that Gene is pulling with a force of 105 newtons. So let's put 105 newtons over here. And it says that Charlie is pulling with a force of 110. So say Charlie's over here, he's pulling a force of 110 newtons. Okay. They want to know what direction this sign is going up. So if this is, say the building is up here and those guys are up on top of it trying to pull it up, the sign's going to be going this direction somewhere, right? Okay, something like that. So we got to figure out what that is. What I'm going to do to solve this is I'm going to go ahead and draw our parallelogram that we've done before with our vectors. We've drawn our parallelograms before, so again, I'm going to go ahead and I'm going to make a parallelogram. So that would mean that this has a magnitude of 105, and I'll go ahead and draw this parallelogram, and that means this has a magnitude of 110 newtons. Okay? From properties of parallelograms, we should know the rest of our angles. We know that opposite angles are equal. So this angle over here is also 30 degrees, and we should know that consecutive angles are supplementary. So this angle right here should be 150 degrees. And what we want to know now is we want to know how my sign is going to be going up. So my sign is going to be going up like this. So what we want to know is we want to know the magnitude and we want to know the direction in which it's going. So what we're asked to find is we're asked to find this angle right here, and we're asked to find the length of this line. Well, if you think about this, all right, we've dealt with stuff before. We have a triangle here on this side. If you look just at this half right here, we have a triangle here that we are given two sides and an angle sandwiched in between. If you remember what we use in that case, your light bulbs should be going off right now in your head. But this is what we use the law of sines, because we have side, angle, side in between. And when we had side, angle, side, we use the law of sines. It was a squared equals b squared plus c squared minus 2 times bc cosine of a. That was a law, or the law of cosine. Sorry if I called it the law of sines, I apologize. The law of cosines we're going to use. Okay, so we don't know. We're looking for a squared. No, a is the side opposite the angle given, so we're looking for that. So a squared equals my other two side lengths, so 105 squared plus 110 squared minus 2 times 105 times 110 times the cosine of our angle, so cosine of 150. We type that all into our calculator. We make sure that it's in degrees. All right, make sure it's in degrees because of that. And then we take the square at the very end, and we get this vector right here has a magnitude, or the side length has a length of 207.68 feet, or newtons, sorry. So this thing is getting pulled this direction, 207.68 newtons, all right? So we also want to know this angle in which we do it, all right? So now all of a sudden we know this side, and we know this angle. To figure out this angle right here, we can do, if we know a side across from an angle, we can use a law of sine. So now we know a side across from an angle. We know this right here. So we can say 207.68 all over the sine of 150 equals 105 all over the sine of, let's just call it x. We'll call this angle x right here, okay? We don't know what direction it's going. So we're going to call this angle x here. And the reason we could use the law of sines, if you don't remember, it was a all over the sine of a equals b all over the sine of capital B. So anytime we have an angle across from sine, we use the law of sines. And then we cross multiply. We'll have 207.68 sine of x equals 105 times the sine of 150. And so we'll have to divide by 207.68. And then take the sine inverse of that. And when we do all that work, we get 15.33 degrees. So what it was doing is it's pulling it 15 degrees this way with a force 207 going upwards. Okay? So that's one problem right there. We use the law of sines and law of cosine. That stuff hasn't disappeared. Here's another case here. It says if there's no motion when forces are acted upon an object, the object is in equilibrium. If the forces are in equilibrium, we are going to draw them tip to tail, and they will form a polygon. Okay? So here's one case right here. It says a traffic light. You guys all know how traffic lights work. They've got two beams like this. And we got a traffic light down here like this. Okay. So they're supported equally by two cable that makes a 160-degree angle with each other. So this would be 160 degrees. If the light weighs 1,200 pounds, what is the tension of each of the cables? So this has a force going downwards of 1,200 pounds. Okay? So if we draw these guys tip to tail, these vectors, so this vector's got to exert a force this direction, and this one's got to exert a force this direction to make sure it holds this guy up. So if we draw these guys tip to tail, we'll have something like this. Okay, so if I go ahead and I take this guy and move it down here, so I have a force here of 1,200, and then I have a force here we don't know that magnitude, and then if I put this guy here, we make a triangle. And again, these two forces have to be the same because it's put this light in equilibrium. So what we have right here, now if we put these, this is 160 degrees right here. The angles that these form is 160 degrees. All right, so the leftover angle right here has to be 20 degrees. I didn't do a very good job of showing you that I drew my picture, but I went down 1,200. Then I drew this going in the same direction, the same amplitude, going this direction. And we know that these guys formed a 160-degree angle, so 160 degrees this way. And then what would be left over, if I had a straight line right here, would be 20 degrees. Okay, so that's how we got this triangle right here. What we notice about, we want to solve for x, and what we notice about our triangle here is that these two are the same, which means that these two sides form an isosceles triangle. For isosceles triangles, we know that the base angles are equal to each other since these sides are equal to each other. To figure what that out, figure what the angles are, we go 180 minus 20, and we get 160. Divide by 2, so each of these guys have to be 80 degrees. Okay? If we know a side across from an angle like we do right here, we can use the law of sines. So we can say 1,200 all over the sine of 20 degrees equals x all over the sine of 80. And we cross multiply and we get 1,200 sine of 80 equals x times the sine of 20. And then divide by the sine of 20. We type that all into our calculator. These two things exert a force each of 3,455.26 pounds. So in order to hold this thing that weighs 1,200. We need each of these cables to be pulling in opposite directions, 3,455.26 pounds. Anyway, that's all I have for you, just showing you some applications of some vectors. I hope this helps. We'll see you in class.